In this video, I'm going to demonstrate how to use the NIRCam Rogue Path tool to avoid the scattered light artifact known as claws. First, I'll give a brief overview on what claws are, why they appear, and how they behave. Then in the second part of the video, I'll walk through how to run the Rogue Path tool and use its outputs to adjust your APT observations to avoid claw contamination. Claws are scattered light artifacts that appear in NIRCam shortwave detectors when bright stars fall within a specified susceptibility region, shown in the plot above. This region is located several degrees away from NIRCam's actual field of view, which is centered at the origin of this plot. So when a bright star lands in that region, its light can enter the telescope through what's known as a rogue path. After bouncing around via several internal reflections, that light eventually reaches the shortwave detectors, creating a characteristic claw-shaped pattern like the one you see here on the right. So this particular example shows a claw artifact on the A1 detector, and you can see it has 3 diffuse vertical streaks spanning the length of the detector. Claws vary in their location, brightness, and overall shape. They can show up on any of the shortwave detectors, and I've included a few examples of them here. Often a claw appears as a single diffuse streak like the one on the left, but they can also show up as multiple streaks, as you can see in the other examples. In general, when a claw is present, it's going to affect about 5% of pixels in a single shortwave detector. Claws can also spill into neighboring detectors. It's not shown here, but in this example on the right, this claw actually extends into detector A2 from A1. Claw appearances are relatively rare. Before we started screening for them in cycle 1, around 10% of observations were affected. But now, thanks to the Rogue Path tool, we can predict and avoid a lot of them, so that number is lower now. Claws are generally stronger in redder filters. In this example, I'm showing a single observation with the same pointing across different filters. You can see that the claw is barely visible in the bluer filters like F090W, but becomes much more pronounced in the redder filters such as 200W. Since the pointing is the same for all of these images, the claw appears in the same general area of the detector, but its shape also varies slightly depending on the filter used. Claws don't shift much with dithering. You'll only start to notice their position on the detector change significantly when you're doing large mosaics. However, they are sensitive to the telescope V3 position angle. The image here is showing the same claw in several observations with a similar pointing. As the V3 position angle increases from left to right, you can see the claw rotate accordingly. And so if this angle changes enough, the claw can actually move off the detector entirely. So what the Rogue Path tool does is it leverages all of this information we know about claws to predict how much claw flux will appear in a given observation. It bases this prediction on the total brightness of stars in the Rogue Path and runs it across all possible V3 position angles. The output from the tool, shown here, displays the predicted claw flux as a function of position angle. Users can then use this information to adjust their observations in APT to restrict the V3 angle to ranges that minimize predicted claw contamination. So in the next part of this video, we'll go through how to run this tool on an example observation and how to use its outputs to modify the observation in APT to minimize claw contamination. So before we get started, I wanted to note a few references here. First, at the top, here's a link to the Rogue Path tool GitHub repository containing the code itself. We also have a JDocs Rogue Path tool page here that goes through how to install and run the tool. And then there's another JDocs page here on scattered light artifacts, which contains more detailed information on claws. And finally, if you have any issues running the code or questions on claws in general, I put a link to the help desk at the bottom and you can make a ticket there. I'm here on the JBoostT Rogue Path Tool GitHub page, and if you scroll down to the README, there are instructions on how to install the code. The easiest way is to just pip install it into your current Python conda environment. You can also install it from source like so. This might be useful if you want some very recent updates or you want to contribute to the code. The notebook I'll be demoing is available in the notebooks folder. So if you want to follow along, you can go to JBoostT Rogue Path tool, notebooks, and then I'm going to be using the NIRCam Observer example notebook. So we'll go ahead and open that up. This notebook is going to show you how to run the rogue path tool on a NIRCam program to get the position angle ranges free from claws. It will also show how to incorporate these position angle ranges into your APT program to ensure the observations are only taken within those PA ranges. So to get started, we just need to import the necessary functions from the rogue path tool. And now the tool itself just requires one input file, the records.json file. If you want to get this for your program, you can just open the program up in APT and then go to File, Export, and check the records.json file, and then you can go ahead and save that. For this demo, I'm just going to use the records file that's already contained in the repository, this APT test for RP tool records.json file. So if you open that file up, what it is basically just a text file that contains a variety of instrument configuration and pointing information that's necessary to inform the rogue path tool. This next section is going to show you how to actually run the tool. The first cell here is just how to run it on all observations in the program. Since that's going to take a while, I'll instead just show you the next cell, which is just going to run it on a single observation. In this case, we'll be running it on observation 5. So we'll go ahead and run this cell using our records file as input. What's going to happen when you run the program is the tool is going to go through each dither pointing. In this case, there's 4. It's going to look at the total brightness of stars in the rogue path and then convert that to how much flux will ultimately show up as is contaminating claw flux on the detectors. This function here is going to plot the predicted claw flux at all possible V3 position angles for this observation. And then the make background report function is going to write out a text file containing the position angle ranges that minimize claw flux. So here's the output from the plotting function. It shows the predicted claw flux at each position angle for every filter in this observation. The horizontal orange and green lines indicate signal levels at 10% and 20% of the predicted background levels respectively. This comes from the JVST background tool. So these threshold lines here are what we're going to use to identify position angle ranges that are free from claw contamination. Typically, you'll want to just use the 20% threshold, but for certain targets, if you're looking at a really faint target maybe, you might prefer the more conservative 10% threshold to base the good ranges on. So the position angle ranges that are below each threshold shown here are saved to a text file. So I'll open up the one for this program here on the left. The ranges printed at the top here correspond to the ranges below the 10% threshold, and the ranges on the bottom correspond to the PA ranges below the 20% threshold. So these are the ones we'll use for this example and are generally the ones you'll want to use. The ranges in this file are determined conservatively by considering all filters and modules together. So if the predicted claw flux in any filter or module exceeds the threshold, the corresponding position angle will be excluded from these ranges. So once you have these V3 position angles that are free from claw contamination, you can add them to your APT files as a position angle special requirement to ensure the observations are only taken within those ranges. So to do this, you can open up your program in APT, navigate to the observation. In this case, we're doing observation 5. And now for each good range we have in our file here, we'll want to add a special requirement by going to add position angle, PA range. Then you'll want to select the V3 PA box and input the range. So for the first one, this is what it will look like. And you'll want to do this for each of the good angles in the text file. So I already have the other ones pre-populated here, and this is what it would look like when you're finished. One note is that the position angle ranges in the text file don't wrap around 0. So right now, 359 to 360 is actually an excluded angle. However, if you have both 0 and 359 considered good in your text file, it's fine to combine those two special requirements together. and do a single special requirement just to make sure you get that last degree. So to do this, you can just modify the last special requirement to go from 308 all the way through to 81. And then you'll want to delete this first one here because it's now redundant, so you can just remove it. And so that's how you can combine a couple together just to make sure it wraps around 0. Now, if you want to check visually that the V3 position angle ranges were input successfully, you can open up the observation in the Aladdin viewer here at the top. And when you do that, make sure you also select this Orient Ranges option. So this plot here is showing you all of the possible V3 position angle ranges in green based on the special requirements we added, and the ranges that are not allowed are in red. So as I click and drag this, you can see the V3 position angle in blue at the bottom there. And just to spot check that we input these properly, you can see that all the way from 308 over to 81 are all green, and this makes sense because it matches the special requirement we put in. And then angles, in the 81 to 92 range are bad, which also makes sense because that range wasn't included in our text file. So that's just a quick way to visually check that you input these properly. Now currently the tool does not take into account target visibility, so some of the position angle ranges shown may not need to be considered. To check which ranges are actually available for a given visit, you can go to Visit Planner here up at the top, click on Reports, hover over the visit, and then click Total Roll Analysis for visit. The top plot here is showing which V3 position angles would be used based on the exposure start time for this observation, and the bottom plot is showing the total number of days each angle is available. So for our observation here, considering that 0 to 81 angle wasn't actually necessary, as you can see that V3 position angle is never actually going to be used anyway. So for this reason, it's worth checking this roll analysis plot because it can save you effort by preventing you from adding constraints that don't actually affect the scheduling. But yeah, that's it. That is how you incorporate the output from the Rogue Path tool into your APT files. Before we end, I do just want to show one other example from the notebook on how to use custom thresholds. So if you scroll down to the bottom of the notebook, I have this other use cases section showing you how to do this. Up until now, we've used the default thresholds based on the predicted background levels to define the position angle ranges that minimize claw flux. But here we're actually going to use a custom threshold. I'm going to use 50 counts per kilosecond to get these ranges. After running the tool, you can access the predicted claw flux for each observation filter and module separately. For example, this line here is showing I can access the predicted claw flux for observation 5, module B, filter F150W. Once you have that, you can identify the position angle ranges below this custom threshold, the 50 counts per kilosecond I'm using here, and then this line just prints out the good V3 ranges based on that threshold, just like we did in our text file. So this method at the bottom might be helpful if your science requires a specific limit, or if you're only concerned about claw contamination in certain filters or modules. And so that's it. That's how to run the Rogue Path tool and apply its outputs to your APT files. If you have any questions or run into any issues, feel free to contact the help desk. Thank you.